Hello students, welcome back. Now let's go to problem 3. Here's the problem. Please stop the playback and read through the problem all the way to the end. The water pollution readings at State Park Beach seem to be lower than that of the prior year. A sample of 12 readings was randomly selected from the records of this year's daily readings, and the study yielded the following data table. We have the mean and standard deviation that came from 12 days. So sample size is 12 and the degree of freedom is 11. Okay, which approximation is more appropriate? This time, clearly, T approximation is coming from the data table, small sample size of 12, and the standard deviation here is coming from the sample, not from the population. All right, let's go to the problem 3.2. Estimate the 95% upper confidence bound. Here's the initial picture. And this is the, a typo here. Upper confidence bound. Okay, it should be upper confidence bound. So the observed mean here and upper confidence bound, 95% here, all the way to actually negative infinity, theoretically speaking, and 5% here. Please appreciate the difference between the confidence interval. Confidence interval has two bounds, left-hand side and right-hand side. And this is a lower bound of the confidence interval, and this is the upper bound of the confidence interval. 95% in the middle, 2.5% here, 2.5% there. That's 95% confidence interval. Now 95% confidence bound, the 95% upper confidence bound looks like this. No lower end, 95% all the way, and 5% here. Likewise, here is lower confidence bound, 5% here, 95% there. This problem is about upper confidence bound. So this is what we want. Don't pay attention to mathematical code here. That's for my programming only. And that's the picture, and this is number we want to find out. So instead of 2.5%, we have to work on 5%. That's the fundamental difference. So 95% confidence interval, we have to work on 2.5%. 95% upper confidence bound, 5%. Same goes for lower confidence bound, 5%. It's just right-hand side or left-hand side. Okay. Here's a solution. The degree of freedom is 12 minus 1, so that's 11. And T statistic is given by n minus center over SE. And that's associated to 5% here. So let's go to the T table. And here's a T table. And 5%, so this column. And that's associated to degree of freedom of 11. 1.796. 1.796. That's how you do it. Flip the denominator to the other side and flip the center to the other side. Here's the computation, and this is what we get. 4.111, that thing. And that is the upper confidence bound. 95% upper confidence bound. 95% confidence interval. One-sided confidence interval goes from negative infinity to 4.11. Okay, all right. This is not a typo. This is a confidence interval, but one-sided confidence interval. The 95% upper confidence bound is 4.11. Okay, so much for interval estimate. Let's go to hypothesis testing. Does this sample study provide sufficient evidence to conclude that the mean of this year's pollution readings is significantly lower than the last year's mean of 4.082? Set of the hypotheses. Okay, this is null. So here we go. 4.082, so equal to 4.082 approximately speaking, that's null. And alternative, okay, pollution got lower. Alright, let's test it. Let's use critical value approach. So hypotheses like this, and here's a reminder, sample statistics, n is equal to 12, okay, sample size, so degree of freedom is 11. Sample mean is given like this, sample standard deviation. And then standard error is given by s over square root of 12. So s over square root of 12. And that's, yeah, as you can see here. Yes. Okay, here's the initial picture. Null, and then less than something, okay. Here is the critical value. And we're going to test whether the observed mean of 3.78 falls here, so that close enough to null, or falls over there, so that is too far away from the null. Close enough to null, the null wins. Too far away, the null loses. It all depends upon the critical value here. Okay, critical value, how do we find it? And let's keep the picture on. So how do you find it? N minus center over SC is a t-statistic. N minus center over SC is a t-statistic, and it is associated to 5% here. Negative 1.796. We looked for this statistic already. Here's a t-table there. 5% column. Degree of freedom 11, 1.796, but that is for the right-hand side. To go to the left-hand side, I need negative sign. Okay, let's solve this equation. Flip the denominator to the other side and flip the center to the other side. We get this computation. Run it, what do you get? We have 3.75. 3.75 something versus 3.78 something. So the conclusion, yes, x bar falls into the null region. Close enough to null, so null wins. We accept null and reject alternative hypothesis. Or some people like to say, fail to reject null hypothesis. A little bit confusing because it's double negation, but historically speaking, that is proper terminology. Let's see, we have enough time left to do some other methods. Okay, they all have some drawbacks, but let's talk about those anyway. Here's probability value approach. Initial picture looks like this. Find out t-score from this observed mean, n minus center over SE, and then from the t-statistics, use technology A to find out the probability here. You cannot use a t-table, or there is t-table, but it's very crude t-table basically. So it doesn't really do justice, but let's try to find out. And here we go. T-statistic, n minus center over SE, and if you run your calculator, you're going to get negative 1.63 something. And as for calculating this, oh boy, that's gonna be a challenge because you'll have to use statistical calculator. I used mathematical computations, so we have something like this, but in general, it's difficult to do. But in any case, we find 0.65 something greater than 5%, 0.05. The problem is, what does it mean? That's the hard part. Conceptually, this method is really hard because of that. You have to understand the idea of this conditional probability. If the null is right, the condition part is given that null is right, the sample mean is so large that it is smaller than the observed sample mean that we reject null. So that is type 1 error. And that probability is too big, then you have to accept null because we cannot reject null hypothesis. That's basically the idea related to this type 1 error and the probability value approach. My suggestion, don't do this unless you know what you're doing. So if you do understand, great. Roughly speaking, this probability value is associated to the probability that null is right, and that's large enough. But then again, that's not really a correct approach either. So I don't know. I just want to discourage students from using probability value approach because the student who chose this method usually did badly in the exam. Hybrid methods, that's a little bit better, but still. A little better, I mean by student who chose this method did a little bit better. That's what I meant. Okay, initial picture is kind of similar to that of the critical value approach, except that this is standard t-curve, now starting from 0, not from the null, and then this is a t-statistic associated to 5% to the left, negative 1.796. And then we find t-statistic given by the observed mean n minus n over NC, and then get negative 1.63 something. Now compare those two, but the hard part is what does that mean? Well, 0 is null basically. So the t-statistic of sample statistic fall into too far away, then too far away from null. Close enough to null, then close enough to 0, then it's closer to null. So it's close enough to 0, so yeah, null wins. But again, that's hard approach. So my suggestion is don't do this unless you know what you're doing. But comparatively speaking, the student who chose this method did generally better than those who chose that method. And students who chose this method usually did the best because that's the easiest to apply. How about the confidence interval method? Well, we found out the confidence bound. That's the observed mean, and then 95% upper confidence bound, we found it. And then try to find out where that null is falling in. 4.082, does it fall here? Too far away from this, so null loses. Fall here, then null is close enough to this, so null wins. And then if you find confidence interval, one-sided confidence interval, it's this blue interval. Negative infinity to 4.11, and then 4.082 fall in that confidence interval. So null hypothesis wins. Okay, we went through extra methods as well.